Hello and welcome to Space Talk with American Astronautical Society. I'm Dr. Amir Gohardani, the host of Space Talk and the editor-in-chief of Space Times. And today I have the distinct pleasure of welcoming Dr. Matthew Greenhouse, project scientist at NASA Goddard Space Flight Center. The topic of our talk is the James Webb Space Telescope mission. Dr. Greenhouse, welcome to the session.
Good morning, Amir.
Good morning. It's really a pleasure to have you here. And this topic is really fascinating to me. It's actually have dominated the space world and media rather for quite a number of years now. So before we dive into this topic, would you please share a little bit about yourself, your background, and your passion for space?
Sure. I'm an astronomer with NASA. I'm stationed at NASA Goddard Space Flight Center near Washington, D.C. And I've been working on the Webb Space Telescope mission since 1997. So it's been a long journey for me that has just ended with the success that everyone is now seeing.
That's wonderful. I want to just chime in here and share an interesting fact that you and I actually graduated from the same university about 29 years apart. I know that you were at that point finishing up your bachelor's in geosciences, and I got my second master's in mechanical engineering. Then you went on to physics, so you did your PhD in physics, and I did my PhD in aerospace engineering. And this topic is very cross-disciplinary, and I think that those different perspectives actually will make it for an interesting talk. Overall, Dr. Greenhouse, why do we need to care about space telescopes to begin with?
Well, space telescopes are astronomers' most powerful tools for looking back in time. Traveling back in time is the stuff of science fiction, but looking back in time is something that we actually do. And it works as a result of the finite speed of light. If you look at a person seated next to you in the room right now, you're not seeing them as they are. You're seeing them as they were a few nanoseconds ago, because that's how long it takes light to travel 1 meter from that person to your eyes. Now, a nanosecond is a really, really small amount of time. So that transmission delay is imperceptible to us. But when we look at objects that are farther away, the transmission delay becomes more pronounced. For example, if we had a magic switch that could turn off the sun and we flip that switch, it would be 500 seconds before we saw anything happen. That's because it takes 500 seconds for light to travel from the sun to the earth. So when we look at the sun, we're not seeing it as it is, we're seeing it as it was 500 seconds ago. Similarly, when we look at the nearest star, we see it as it was 4 years ago. If we look at the center of our galaxy, we see it as it was 25,000 years ago, and so forth. And so astronomers use giant telescopes in space to look back in time to understand how the universe formed and evolved.
Very interesting. So, in other words, when we look at the night sky, we're actually looking back in history in some ways.
That's right.
All right.
Now, the Webb mission was conceived in the early 1990s to collect the dots, if you will, between the famous image shown at the upper left, which is an image of the oldest light in the universe. It was obtained by NASA's COBE satellite. A Nobel Prize was awarded for this image. In those colored blobs that you see in the image are temperature inhomogeneities from which galaxies will eventually evolve. Now, about the same time as COBE obtained this image, the Hubble Space Telescope was launched, and it produced the famous image shown at the lower left, which is called the Hubble Deep Field. And that was the deepest image that the Hubble had taken at that time. So that was an image of Hubble looking as far back in time as it could. That Hubble Deep Field image shows us what the universe was like when it was about 1 billion years old. And the Kobe image shows us what the universe was like when it was a few 100,000 years old. And between the Kobe epoch and the epoch seen by the Hubble Space Telescope, shown on this cartoon, is a mysterious, poorly studied epoch known as the cosmic dark zone. And this cosmic dark zone is of great scientific interest because it is the period in the evolution of the universe when the first stars in galaxies formed. That epoch is poorly studied because we haven't had the right type of telescope in space to study it. And that was the original impetus for the Webb telescope mission.
Very interesting. And I guess we have a little bit of a snapshot into diving to the stars here.
Yeah, when Hubble took its famous image, deep field image, it did so by staring at a single spot in the sky for a long, long time, a couple of weeks, leaving the camera shutter open, if you will. And this is what Hubble saw. In almost everything in this image is a galaxy. And so we haven't yet seen in this image the epic of galaxy formation. There are still more galaxies to see deeper into space, farther back in time than Hubble is able to see. And that is because Hubble lacks the features that are needed to observe the cosmic dark zone. And we've put those features into the Webb telescope.
Mind-boggling. I guess at this point, it's interesting to learn more about light, and probably you can shed more light on this as we move on.
Well, the light that is emitted by those first galaxies, by those primeval galaxies, is emitted in the ultraviolet part of the spectrum. But as that light travels to us through the expanding space, the wavelength of the light is stretched into the infrared part of the spectrum. So to see that light today, to see the light from those first stars and galaxies, we have to build an infrared telescope. And that is one of the key differences between the Webb telescope and the Hubble telescope.
Yes, and so if for those of us who need to refresh our physics and the electromagnetic spectrum, can you talk a little bit about the
Sure.
differences here?
Everything we know about the universe is transmitted to us in starlight. And so to study the universe, astronomers need access to all of the light so that we can get all of the information that it contains. Light comes in an infinite spectrum of wavelengths, from infinitely short to infinitely long. So things like gamma rays, X rays, radio waves, they aren't different things. They're just different wavelengths of light, different colors of light. Now, most of the light is invisible to our eyes. Our eyes have evolved to just be sensitive to a very narrow slice of this spectrum called the visible spectrum. And it matches a transmission window in the Earth's atmosphere. So light within that narrow visible spectrum can reach the surface of the Earth through the atmosphere. And so our eyes have evolved to be sensitive to that, but there's a lot more light to see. Shortward of the visible, one has the ultraviolet spectrum. Our eyes can't sense ultraviolet light, but our skin could be burned by it if you stay at the beach too long. The Hubble was designed to operate in the ultraviolet part of the spectrum and the visible. In contrast to Hubble, the Webb telescope is designed to operate from the red end of the visible into the infrared. Our eyes cannot see infrared light, but our skin can sense it. If you hold your hand near a warm stove burner or a radiator, you feel the heat on your skin. What's happening there is your skin is sensing the infrared light that's being emitted by the warm object. So that infrared light capability that we put into the Webb is crucial to seeing the light from those primeval galaxies, because all of that information is in the infrared part of the spectrum. But that infrared capability enables the Webb to do lots of other science that are important parts of the mission.
Yes, and part of that, I guess, here is to try to see the birth races of stars, correct?
Yeah, the spaces between the stars in our galaxy, the so-called interstellar space, is not an empty vacuum. It's filled with giant clouds of molecular gas and atoms and ions and dust particles. And this is a picture of a giant molecular cloud in space. Some stars have formed here which are putting out a lot of ultraviolet light. And that ultraviolet light is ionizing the molecular hydrogen of this cloud, causing it to glow and produce this visible nebulosity. During the early part of the Hubble mission, Hubble observed a part of this nebula. And if you could advance to the next, there you go. So Hubble observed part of this Eagle Nebula to take this famous image called Pillars of Creation. And what you see here are filaments of molecular gas, molecular hydrogen, and those filaments are opaque because there's lots and lots of dust mixed in with the gas. Now, when we observe this same field in the infrared, if you could go ahead and advance that, the longer wavelength infrared light can penetrate the dust. It can see through the dust. And that allows us to study with more clarity the star formation action that's happening inside this dusty gas. And so this is just an example of how the Webb's infrared capability can help us do solve science problems very close to home.
Wonderful. And
Now,
can you
now
shed a
we
little bit more light on the planetary systems?
sure we know the basics of how stars form. These giant clouds of gas in space collapse onto themselves with self-gravity. And as they collapse onto themselves, the pressure inside the cloud starts to go up. And as the pressure goes up, the temperature goes up. It's much like when you fill your bicycle tire at a gas station, the tire gets a little bit warm when it's fully compressed. Well, the same thing happens in these clouds, except in the cores of these clouds, it gets really, really, really warm to the point where nuclear fusion can occur. And then that is how the star is ignited. And as shown on the upper right of the top row of this diagram here on the left side of the chart, when stars form, they are typically surrounded by a disk of material that is left over from the star formation. And those circumstellar disks, as they're called, are of tremendous scientific interest because they are the birthplaces of stars and planets like our own. And as planets form within these disks and orbit the star, the planets sweep up material in the disk to cause them to take on this sculpted appearance. And at the upper right, you have radio telescope imagery of these sculpted debris disks. And so by observing these disks with high resolution imagery, we can infer the presence of planets without even being able to see the planets themselves. And the Webb will do a lot of study of circumstellar disks to understand how planetary systems like our own form and evolve.
Yes. And so, and this is to that point as well, right?
Yeah. Now here we have at the left an artist's rendition of the debris disk surrounding our star, the sun, alongside a map of where that debris actually is. These are the so-called Kuiper belt objects or trans-Newtonian objects, and they are chunks of pristine material left over from the formation of our solar system that are orbiting the sun in the outer solar system. So they're of great scientific interest. And the Webb, we've put special non-sidereal tracking capability into the Webb to allow it to observe these Kuiper belt objects and the planets of our outer solar system. And if you advance this, recently we got our first image ever of a Kuiper belt object. This image is from NASA's New Horizons mission. And when New Horizons finished, New Horizons was a Pluto flyby mission. And when it finished the Pluto part of its mission, we sent it out to observe this Kuiper belt object. And this is what we saw. And it turned out to be two objects fused together. And we've since determined that this can form as a result of a very low velocity collision shown in simulation here of just a few meters per second can cause objects like this to fuse together with neither object being destroyed in the process. And this is of great interest to theory of planetary formation, in which planets form by successive agglomeration of smaller particles into larger ones, eventually forming a planet over 10 to the 8 years or so. Let's go on. All right. With that non-sidereal tracking capability, the Webb will study the outer planets of our solar system, Jupiter, Saturn, among others. And some of the most interesting work that the Webb will do in the solar system is on moons of planets, such as Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. On Jupiter, Webb will study the Great Red Spot. This is a storm that's raged on the surface of Jupiter for more than 400 years. Today, we see that red spot is shrinking, and the Webb will perhaps help us understand why it's shrinking. And the Webb may help us understand why the red spot is red. We still don't know for sure why the red spot is red. The Webb will search for small moons of Saturn that were too faint for flyby spacecraft to have seen. And one of the most interesting things Webb will do in the solar system is to look for water. Liquid water in the solar system is not limited to the Earth. And in fact, most of the liquid water in the solar system may not be on the Earth. Moons of Jupiter and Saturn, Europa and Enceladus, are believed to contain vast oceans that are covered by a thick crust of ice. And when tidal forces act on that ice, the ice cracks and it results in a geyser formation in which ejecta escapes through those cracks from the underlying ocean. And at the lower right, you see an actual image from the Cassini spacecraft of this geyser phenomena. And the Webb will study that ejecta spectroscopically to understand its chemical composition and so that we can learn more about the underlying oceans. It's possible that life could exist in these oceans. We know from studies of the mid-Atlantic ridge on the Earth that life can exist completely independent of the sun, thriving on chemical energy. And the same thing could be happening in these oceans. And so this will be of great interest when the Webb gets these data.
So a motivational factor here is basically to look at partially the ice, and similarly to what we've been trying to search for on Mars, right?
Sure. We'll be looking at the material that's escaping through those cracks in the ice, and we'll be measuring its chemical composition to learn about the chemistry of that underlying ocean. Now, when I was a graduate student, there were no planets known outside the solar system. And today we believe that for all practical purposes, all stars have planets. We've identified more than 5,000 specific exoplanets to date, with the implication that there are tens of billions of habitable worlds in our galaxy. Now, we don't know that they're inhabited, but we believe that they are habitable. And so we have learned how to search for life on these exoplanets by studying their atmospheres. So the search for extraterrestrial life is no longer the stuff of science fiction. It is very much a major science objective of NASA, and the Webb telescope will be the next element in that process. So, how do we search for life on an exoplanet that we can barely see? We do it by obtaining spectroscopy of the planet's atmosphere. Spectroscopy is a process where we spread the light out into its component colors by special optics so that we could see the emission and absorption of light by individual atoms and molecules in the atmosphere of the planet. So on the upper right, you see a spectrum of Mars, Earth, and Venus. So what is that squiggly line? That squiggly line is a plot with brightness on the y-axis and wavelength on the x-axis. And all those variations in brightness at different wavelengths are emission and absorption of individual atoms and molecules, for example, in the atmosphere of the Earth. So if the Earth had no atmosphere, that squiggly line that you see would just be a flat line. But the Earth does have an atmosphere, so that squiggly line shows us what the chemical composition of the Earth's atmosphere is. So we will be obtaining these spectra on exoplanet atmospheres to look for chemical species that are indicative of life. So look for chemistry that would be unexpected as a result of abiotic processes alone. How do we do it? We do it with a process called transit spectroscopy, which is shown by the cartoon on the lower left. Many of the exosolar systems that we will be observing will be seen edge on. So imagine that we have the configuration shown in that cartoon, where we have a star and we're looking at it with our spectroscope, and a planet wanders into our line of sight between our observatory and the star. And we take a spectrum. What do we have? We have a spectrum of the star plus the spectrum of the planet's atmosphere. Now we just wait a little while for the planet to move out of the way in its orbit about that star, and we repeat the measurement. Now we have a spectrum of the star all by itself. We subtract the two, and voila, we're left with a spectrum of the planet's atmosphere. Now I'm making it sound easy. It's actually profoundly difficult. It requires very high precision photometry, a few parts per million precision photometry. But this has been turned into an exact science with the Hubble Space Telescope. And the Webb will do a great deal of this work on exoplanet atmospheres. The Webb will be primarily studying exoplanets that are somewhat larger than the Earth. The Webb can detect water vapor on an exoplanet that is a few times the size of the Earth. When we're looking for extraterrestrial life, why do we care about water? It's not because alien life might get thirsty and need something to drink, but rather in order for the organic chemistry of life to occur on a planetary scale, one needs to have a liquid solvent available on a planetary scale, and water is what we're most familiar with.
Wonderful. And regards, I think you touch upon some of these elements, and I ask you to please talk a little bit about the cryogenic
Sure,
and the mirroring as we move forward here, if it's
sure.
possible.
Okay. If you could actually go back one slide.
Mhm.
To when we first put pencil to paper on what did we have to build to do that science, we realized that we needed to build an observatory that had 7 times the light gathering capacity of the Hubble Space Telescope. And we also needed Hubble's ability to see fine detail, angular resolution, as they call it. But we needed that in the infrared spectrum, and that also requires a giant mirror. And then, as we mentioned, we needed this observatory to be able to observe in the optical to mid-infrared spectrum. So when we realized that, we realized that we had two enormous problems that almost stopped the project completely in its tracks. And as well as you can surmise, we did solve those problems. And they were that to get 7 times the light gathering capacity of the Hubble Space Telescope, we needed a primary mirror that was bigger in diameter than the biggest rocket. And then to make an infrared telescope, one has to make the telescope very cold because anything above absolute zero emits infrared light. If you had infrared goggles on right now, you would see your body glowing in the infrared. The walls and floor of the room would be glowing in the infrared. And if we didn't make the Webb telescope very cold, it would be blinded by its own infrared emission. How cold do we have to make it? Really, really, really cold, almost minus 400 Fahrenheit. And then and now, there is no mechanical refrigerator powerful enough to cool something as big as the Webb to such a low temperature. So those are the two problems that we faced. To make, you can go to the next chart, to make the observatory to deal with the large mirror, we had to adopt something called a segmented mirror architecture so that the mirror could fold up inside the fairing of the rocket. And then as we launch this telescope into space, it has to unfold like origami. When we launched the Webb, we sent it to, the Webb does not orbit the Earth the way the Hubble Space Telescope does. Or we sent it to a special spot in space called the second Lagrange point of the Sun-Earth system. It's about 1,000,000 miles away from Earth in the anti-sun direction. And shown on this diagram, we went out there on what's called a direct transfer trajectory. So we did not orbit the Earth even once. And to unfold the telescope from the rocket, it involved 50 major deployments and 178 release mechanisms. All of those were single points of failure. And every one of them had to work perfectly because the Webb telescope at this L2 point, 1,000,000 miles away, is too distant for the astronauts to ever go to. And so if any of these deployments didn't work, the mission would simply be a failure and there would be no way to recover it. Let's keep going. Now, to make the telescope unfold from the rocket, we adopted something called a segmented mirror architecture. So instead of building a single mirror, we built 18 hexagonal segments that are mechanized in 7 degrees of freedom, the 6 that you're familiar with, plus radius of curvature, so that they could be individually adjusted to play together as if they were a single mirror. So when we first pointed the Webb at a star, we had 18 individual telescopes. And we have to adjust the segments of the mirror to superpose all those images onto each other. And then we had to use special interferometric optics to adjust the segments to make them extremely coplanar to within a small fraction of the wavelength of light to eventually produce what amounts to a perfect image. This procedure was very successful, and the Webb is exceeding its image quality requirements by a lot. This illustration shows how the telescope unfolds. You saw the secondary mirror unfold, and now you're seeing the wings of the primary mirror unfold, much like a round drop leaf kitchen table.
Fascinating. And I guess this
But
is the sun shield.
yeah, let's talk a little bit about that sun shield. The Webb sun shield is literally the size of a tennis court, and it has an SPF of 1,000,000. So if you had this sun shield on the beach, you would be very, very well protected. It's made of 5 layers, as you can see, and each layer is made of a heat-resistant plastic-like material called Kapton. Each layer is thinner than a human hair. The sun-facing layer is coated with silicon, so it really does look pink like that. The rest are coated with aluminum. And you'll notice that the sun shield has a special curved shape that's crucial to giving it that SPF of 1,000,000. And that those of you who sew know that to make something curved from flat cloth, one has to have a lot of seams. And so each layer is actually a quilt of 50 pieces. And the seaming here is not done with needle and thread, but rather with thermal spot welds. But there are 7,000 inches of high precision seaming involved to make this sun shield. This was the highest risk part of the whole Webb mission, designing the sun shield to get that SPF of 1,000,000, and then figuring out how to fold it up and deploy it reliably. This was the toughest part of the mission, the part that we were most worried about, and it did work perfectly for us.
Yes, it did. And yes, this is the
All
last
right.
view.
Here we're down in Kourou Launch Center in French Guiana. We're in the vertical assembly building. So we're riding up an elevator alongside the Ariane 5 rocket. There are work platforms set up at various points along the rocket, and we're going to the top where the Webb telescope is being joined to the launch adapter on the rocket. So this is the last view of the Webb telescope on Earth. And this integration was done successfully. As you can see, it's a very clean environment. And on this rocket, the fairing or nose cone is integrated axially like that. So that's the Webb buttoned up for launch. And the Ariane 5, the French rocket, is rolled out to the launch site. And then we launch.
And we have engine start. And liftoff.
Décollage.
Decollage, liftoff. James Webb begins a voyage back to the birth of the universe.
All right, the rocket worked perfectly. We got a great ride out to the L2 point. The course corrections on the way to the L2 point were smaller than expected, so we have a lot of propellant on board to do the mission. We have at least 20 years of propellant on the Webb to do the science mission. This is one of the early release images from the Webb telescope, and it illustrates a lot of the power of the Webb. This is an image of a giant molecular cloud like the Eagle Nebula that we spoke of. So all of this sort of brown material is molecular gas that is mixed with dust. Newly formed stars have been formed here, and UV light from those stars is breaking up the molecules in this cloud, and you can see hydrogen gas streaming off the cloud into space. There are a lot of newly formed stars seen here embedded in the cloud. Some of these sort of yellow point sources that don't have diffraction spikes are newly formed stars that are still embedded in the cloud. You can see this pillar-like phenomena that is forming like those pillars of creation that we saw and previously, and you can see the enormous detail that the Webb imagery provides. It's a much higher angular resolution than we've ever had before in the infrared. The Webb is literally giving humanity its first high definition view of the infrared universe.
Yes, Dr. Greenhouse. I actually wrote a recap of 2022 article for Aerospace America, what I called the article "Seeing the Unseen," and this particular image was there, and it just magnificent to see this level of detail, and
Yeah.
it's just fantastic. Thank you for walking us through this, and we have arrived at almost the last slide here, and it's very interesting to me to learn a little bit about how you perceive the life of a scientist. Can you, it could be a generic statement, but how your particular journey has been.
Well, it's been great fun for me. I started out as a geologist, and I eventually, after I got my degree in geology, I got interested in astronomy and planetary science and stuff like that. And so I decided to get my PhD in astrophysics. And then I did my postdoc, the first job you get after you get your PhD as a scientist at the Smithsonian in Washington, where I worked on an infrared. I worked on a European infrared space mission called the Infrared Space Observatory. And working at Smithsonian, I also learned a lot about public outreach and communicating what we do as scientists to the public and the importance of that. And then I eventually moved up to Goddard Space Flight Center, where I've been since 1996. So I guess I'm at the end of my career as a scientist, as I'll be retiring soon. But it's been a tremendous journey for me. I spent most of my career working on this one project. And so that's a little bit unusual. Most scientists would work on a number of shorter duration projects over their professional lifetime.
Yeah, I can imagine the satisfaction that you had seeing an image like the previous.
Yeah.
It's really a pinnacle of achievement. So congratulations on that. For those who are interested to get into these type of what are the life of a scientist or astrophysics or geosciences or anything related to space, could you share some career tips with them at what they can?
I certainly can. First, I want people to understand that the folks who work on projects like this and do this kind of work come from all walks of life, in all backgrounds. Projects like this involve every engineering discipline that exists. It involves chemistry, physics, all kinds of complex management, systems engineering, even lawyers are involved. And so if your interest is in this sort of work, in these sorts of missions of discovery, no matter where you come from or what you look like, you should have the confidence to jump in and try and get involved. If one needs to go to college, study whatever you love, but if that happens to include science, engineering, or math, you should really, really consider aerospace as a career. If someone asks you what you want to do when you grow up, if you say, I want to design the career objective, you can get a taste of it by applying for a NASA intern program. We have internship programs for every stage of career, from high school to university faculty. And there's one-stop shopping for internships at NASA. I think the website is interns@nasa.gov or something like that. And we also have something called citizen science, where if you happen not to be a professional scientist, but you want to get involved, you're kind of an amateur scientist, you can get right involved with Webb science by working with NASA's Citizen Science program. And they also have a website for how to get involved.
Thank you very much for sharing. This has been a really interesting talk, and uh, I had the pleasure to share this journey with you and really see your perspective working on such a fascinating project and mission that I guess has to play and will play a significant role in our lives, not only now but probably much more in the future because of the discoveries it will make. So, thank you so much for taking your time, and it was a pleasure talking to you, Dr.
Thank you for having me.